Good morning, everybody. So as he was said, we are like the entire Dynamics Spain operation here, and today we're going to talk a little bit about the latest work we have been doing regarding unpacking. So a little bit the outline of the talk is going to go through just first of all give an overview of the kind of environment we have for our tests, where we build our heuristics and our algorithms to deal with unpacking. And then the three next points are pretty much Jose's research, where he just came up with some new heuristics to try to quantify properties of the unpacking process in a way that allows us to know more precisely when it's done. So that's the trunk of the talk. So given that we are going to be talking what we decided to kind of like relate to genetics in the process of unpacking, and in this part of the world the idea of genetics and evolution seems to be a bit of a sometimes hard concept for some people. We decided to go ahead and create just like a condensed version of the presentation for people, you know, for creationists. So from the creationist point of view, unpacking happens so that you have something packed, then the spaghetti monster comes and you have something unpacked. Thank you for your attention. For the rest of us, the process is a little bit more complex. So first I'm gonna talk about the environment that we are using. As you can guess, if you know what Box is about, it's based on Box. Box is a CPU emulator. So I'm gonna tell you what we did and then why we chose those things. So we decided to go with a CPU emulator for most of our work. And of all the available CPU emulators, we chose Box. What we did then is we exposed the instrumentation interface that it has and substituted its Box debugger by a Python command line. That allows us to work really, really comfortably with all the functionality that Box exposes to control the execution. And now, why we chose this path? Well, regarding CPU emulation, when we started this, which was like already a few years ago, time flies, hypervisor technology wasn't really available in a way that we could just not grab computers with hypervisors and use them for our unpacking. So we needed to do something, you know, rely on software-based tools for systems. I really like the idea of going with CPU emulator because of the level of control that it gives you. Really, like something like Box or QEMU allows you to control like execution at the level of instructions or basic blocks, depending then on the implementation of the specific tool. But a really, really good control, like fine granularity of everything that is going on, and that's something that it really turns me on in a way. So then most anti-debugging tricks, the idea behind most of them, if you generalize them a lot, is find differences between the real system and the system under supervision. Like if you're running a debugger, sometimes the environment is going to be slightly different as opposed to the real system. In the way it handles exceptions, in the memory layout, in the heap implementation or backend that it uses. So most anti-debugging tricks, what they try to do in a generic way, is just finding those different points between the real system and the supervised one. So working with a CPU emulator and just building a totally standard system on top of that allows us to pretty much disregard most of these checks, because we're going to be running a full Windows with these full APIs, the full DLLs. There is nothing really to detect other than discrepancies in the CPU emulation. But Box is not perfect, but fairly good. So although like there's been some research in the last year, something done by the Politecnico de Milan, where they analyzed a set of like QEMU, Box, and a few other CPU emulators to find instructions that are not properly emulated. Box still came out on top. It had few instructions that were not emulated as a real system, but it still did a pretty good job. So, I mean, for our tests, we have been able to deal with everything. It runs a full Windows XP. Windows doesn't even know that it's being emulated, so I would say that's fair enough. So, why we went with CPU emulator and not sandboxes? Well, I'm really lazy. And just the idea of having to implement more and more APIs just to get to, asymptotically approach a real OS doesn't seem like something I want to spend much time doing. I mean, I'm up for job security, but not that way. So, because when you develop a sandbox, pretty much the only thing you're trying to do is catch up with what a real system has. So obviously, if you can survive with a really reduced set of functionality, you're going to have something really, really light. But if malware, and usually malware does that, knows that it's running a sandbox, it's going to try to use everything that the sandbox doesn't have. So in the end, you end up developing pretty much an alternative OS. So it's like, I don't want to do that. So sandboxes never really made it for me, and then they have other issues. So of all the CPU emulators, why Box? Well, when I was looking at them, there was QEMU Box and a couple of others. I spent like a couple of days looking at them, and Box was the one that I found had like a really nice instrumentation interface that allowed me to control everything that was going on in the machine, from the hardware level to like software interrupts, to when an instruction was fetched from memory accesses, everything. In addition, with a really nice callback interface. So whenever any of these events happen, I could actually register a callback and get notified. And then as well, in the last couple of years, finally some feature that was only in one branch was ported to the main trunk, which was the snapshots, which is really, really comfy, because nowadays we have this totally ready system with one of our agents inside running that is waiting for data to come. So you just like spring up the snapshot, send the file to unpack, and everything is booted, because Box takes like a few minutes to boot a Windows, so you wouldn't want to be booting it all the time. So I don't know, it has a couple of nice bells and whistles, and it works really well. And then why I ended up embedding Python into Box, although it makes it slower in some ways, it makes my development cycle so much faster. Because before that, every single test you wanted to do, you had to recompile the whole box with the new instrumentation, with the new fixes, and that was a pain in the ass. With Python, I could just like dynamically hook the events I wanna monitor, like instructions, memory accesses, and dehook them, and then Box runs native speed. And when I hook them, it just goes through a bit of Python overhead, but it still gets like for like 100, 200,000 instructions per second, easy. Depends a lot on the actual environment and what I'm doing, but for me, enough performance. And anyway, it made just I ended up doing in an afternoon what I had been doing like 2-3 weeks programming in C and recompiling the whole time. So it was a good thing. As a general overview of how Box looks like, well, it emulates the CPU and emulates the subsystems, and it exposes a series of events that you can register for regarding memory and CPU processing, fetching instructions, decoding instructions, executing, and then memory accesses, and then hardware input-output. So my main work was exposing all this instrumentation interface in a way that Python could use it dynamically, and then substituting Python box debugger with a Python command line. So before that, I was limited to just setting breakpoints and reading memory with the box debugger, which is okay, but very limited. And nowadays, I can just write full-blown scripts and make them send emails and do a RSS feed of something if I want. You know, I can use the whole Python inside Box, even for totally useless things. So that's cool. Then obviously drawbacks, and this is no surprise for anybody, it is, speed is not the best thing. I mean, I'm emulating a full OS, and it goes through everything that the OS has to do, context switches, all the processes, all the kernel. So speed is not the greatest, but it's not an issue for us, because this system is working on big machines, and it's nothing intended to be working on a client machine or a user computer. So from that point of view, it's not really a big issue. And there's a few things we could do to optimize execution, like, for instance, port everything to C or C++. But right now, it's more like this part is more like the researchy part. And then we have to put some effort on removing noise. I mean, if you are implementing a sandbox, you can implement just the functionality you want to capture, you want to listen for. Or if you're working with an API monitoring tool. But in something like Box, you see everything that happens in the OS. So in order to actually pinpoint the functionality, a single process and the unpacking execution, the unpacking process going on in that task, you need to remove everything else. You need to be aware of all the processes, you need to be aware of the memory spaces of all the processes when the kernel kicks in, and be able to remove all of this. So that was just like a few lines of Python, but you have to do it. So once we had all of this system, we started building our unpacker. And the idea is I wanted to do something that was as simple as possible, on the line of being really, really lazy, big thing. I didn't want to have to look to every single packer thing, specifics, how it does this, how it unpacks, how it decompresses, the algorithm this, the anti-debugging tricks, nothing. I just wanted to do one algorithm that tried to capture the workings of as many packers as possible. So the idea was to have just that one algorithm, or something, with a couple of heuristics, but really generic. So if you have thought about the unpacking process, like pretty much it's just, you launch the packed executable, it does some magic, the version for creationists. And you have something that is unpacked, and then you just want to be able to capture that thing that is unpacked. If you are able to model this kind of pattern in a way, then you're on good path. So steps like this would capture most of the packers while they are unpacking. Although, note, there are a few packers that do their work dynamically. So there is not a single point in time where the whole application is unpacked in memory. They do it on demand. So we don't capture that kind of functionality with this, but I would say that's a really, really small percentage of all the packers used out there. But there are. So there's a couple of other tricks we could try for that, but we are focusing just on the kind of like traditional packed process where you have at some point in memory, there is like the full-blown unpacked application. So on those lines, before we got there, there were a couple of other things that we tried. And I just want to walk you through, because if you give it a thought, probably you would come like, oh, we should try this. And there is like a few drawbacks with some of these things. One of the first ones that I've tried that gives decent results will be the tracking execution into dirty memory. I call dirty memory anything that it has been written to. So if you're monitoring the application, you see that it writes to different pages, and then execution jumps into one of those pages. That's a good sign that something is going on. There's, self-modifiable or new code that appears in a page and you're jumping to it. Could be the original application, maybe not. Because sometimes, you get multi-stage packers that write their own code and keep going, write their own code, keep going. So, but as a first thing, it actually works with some packers. Then you can build some heuristics on top of that to try to capture this multi-stage thing by the amount of code that you see. But ended up working for a fair amount, but there was still like a big percentage that weren't captured with this functionality. So that idea was kind of like, okay, let's try something else. Then trying to capture long jumps, or any combination of these, by the way. We tried different things. Trying to capture long jumps would be like, if you imagine how the unpacking process goes, there's a lot of like small loops as it's decompressing and decrypting, deobfuscating, whatever, most of the code, and eventually it's going to be a longer jump, if you can quantify it in a way, to the original entry point. So if you can capture that kind of longer jump in a way, just by even measuring the distances in memory from one jump to another, and you combine that heuristic with others, that is kind of a good sign too. It yields some results. That's mostly for detecting the original entry point, but it helps as well to try to determine when the application has been totally unpacked. Then instruction pointer execution jump patterns. It will be a little bit more, let's say, solid than the previous approach. This would actually be looking at the jump patterns, obviously. Try to quantify the distances in a window of time. So to capture that there is a loop going on, because if you imagine like the unpacking process is going to be few, probably, short loops, depending on the packer. And then when finally the application kicks in, it has like a big body of code, and where the execution is not necessarily tied to these small loops. It just jumps more like a function, wait loop, function. So if you can capture these like shorter loops and then a bit more random, which are different methods like time series analysis that you can do for these things, that's a good heuristic too. You have a question?
Yes, I'm thinking things like code and mice or things. Are you really interested in getting the full executable, or is that something you can analyze?
Something you can analyze. We don't really care about some of the nice reconstruction things. That's a good point. So that was another thing that gives some results, but nothing crazy. So another thing will be monitoring APIs. Like, as the unpacking goes on, you will see load library, get proc address, maybe, if they don't have any shellcode-like techniques to find them, but or use them. And then virtual protect, and a couple of others. And then you could think, okay, if I start seeing like the rest of, a wider selection of APIs being used, I could assume that the application is unpacked. But again, there are some packers that use really extended sets of APIs, sometimes because they need them, sometimes to just fuck around with you. So it's nothing that you can really rely on. It will be another heuristic, but there is no way of combining them properly. And then looking for entry point patterns, looking for like typical entry points from different compilers or different tools. again, that yields some good results. There were some generic unpackers that were based only on this principle, and in the past they used to work really well, but nowadays some packers actually embed pieces of code that look like entry points from clean applications, unpacked applications, or compiled applications, and just to trick you that, yeah, I'm done, haha, no way. So most of these things did work, but in a way they were just like not the right thing. They were just too specific. So we wanted to have even something more generic. So that's what we're going to talk about. We try to capture this execution loop, and nowadays we have, that's the thing that he came up with, an heuristic that allows us to quantify code, and in that way determine when the unpacking might be actually finished. So we still we have a couple of things to sort out, like like a way of measuring the quality of our unpacking. That would be, we have something that kind of tells us something on the lines, but it would be nice to have something more solid about the final result. How strongly we think that it will be unpacked because of different properties. Still working on that, but then execution time. There's a couple of things we could do, so we're not too worried about that. But at some point, it would be nice to put some effort. And then issues to solve, removing even more junk, more data, more obfuscated code. Because in the end, we end up with a snapshot of what executable code, but still there could be leftovers of the packer there. So there is a little bit more cleanup that we could do through analysis. But so far, we're getting really good results, and these are points to improve on later on. So I think now it's the turn for the good stuff.
Really?
Well, we'll see about it.
So sound is okay? Okay. So as Aaron said, the whole thing, the unpacking, is working over some kind of heuristics. And before talking about the heuristics and how we use them and everything, we need a bit of background. We are all reversers, but just refreshing a few things. So we will start talking about compilers and the relation between binaries and common things between them. So I will be considering that, for example, a binary and an executable is like the product of a source code with a compiler and some flags for the compiler. So if you change any of those elements, you get a slightly different binary or a quite different binary. But in any case, we know that if we have been doing reverse engineering, we always have this kind of, I've seen this before. So in all executables, we will have we can recognize this kind of common patterns. That's what we will be, we have been studying a bit, and those common parts, what we have there. So for example, if we have binaries of different compilers, we can, it's a really general description, but compilers generate code based on functions and imports. Imports are just jumps or calls, but the function, if we try to imagine a generic function, I bet that most of us will imagine a function dealing with arguments, with the stack variables, with push pops of registers, and calling other functions. There are some other things that you can imagine, but those are probably the most common. So what are we trying to say with this? For example, that this piece of code, anybody could, it's going to be too risky to be 100% sure of which compiler generated this. Why? Because it's too common. And why is that important? That we are going to have sequences like this one, for example, in many binaries that are compiler generated. So what happens when we have the same compiler and different source code or slightly different flags? So we have code sequences that still remain, of course. We are talking about different sequences that are not general to all executables of different compilers. So in this case, I put this example here. I'm pretty sure you recognize this. This is a typical Borland loop for zeroing memory on the stack for buffers and so. So this is a really typical pattern of Borland compiled binaries. So this is, in some way, this gives us information that this binary was compiled with Borland, and this piece of code is part of a function. So we were talking about compiler types, what we mean with that. We're talking about those common patterns that match functionality that allow us to recognize that in a piece of memory there are some functions inside. So whatever, what we were saying before, the exception handling, arguments, whatever. And for the title of our talk is the selfish code. This comes from a book from the 70s about genetics. And I really like the description of the definition of the gene that is made in that book, that is this one. A gene is any portion of chromosomal material that potentially lasts for enough generations to serve as a unit of natural selection. Basically, it's like a small part of a chromosome that lasts over your sons and grandsons and everything. So what about our executables? What if we pour this concept to binary executables? So we rewrote this definition in, to adapt the binary world. So we will define that our genes, the compiler or whatever you want to call it, genes, are any portion of binary opcodes that potentially last for enough binaries and that will serve us as a unit of compiler code detection. That's the main point of the thing. Be able to detect code that has been compiler generated. So how are we dealing with genes? How can we know what's a gene, what's a good gene, translating this, what's a good pattern, what's a bad pattern? First of all, if we try to imagine these common patterns in functions, compiler-generated functions, and we try to look for those patterns inside the packed binary, in most cases, those patterns are not going to be anywhere, or just we're going to have really few hits of the thing. Obviously, well, we'll talk about this later. There are packers that have a lot of compiler code, for example, Armadillo, but as we'll see later, this is not a problem. And as an example, this is a really colored Excel table. This is actually, each column represents some of the tests we were making with those patterns, those genes. And in green, you could see like it's like an indicator of really a high amount of presence of that pattern. The orange is like, it's not zero, but just really few hits. And in red, it's like completely zero. There's no presence of that pattern. So as you can see, there are like columns that are tied to most Borland, others that are tied to GGC or Visual Basic. And as a funny thing, here in the down right part, you can see this Visual C. We used the protection ID. I don't know if you guys know, probably yes. It's a kind of PID, but it works a bit better in compiler detection. So those samples, like down right, protection ID tagged them as a visual C, but based in the patterns we got, they resulted, looking by hand to them, they resulted to be like GCC for Windows, the Ming compiled binaries. So this gives some feedback that the thing is kind of working to detect compiler generated, and also have information that is going to be quite useful for the later analysis of which compiler we are dealing with. So to have like an idea of how this works in a single file, this is a random executable file, and I just used it. This is a screenshot of, I think it's 010 editor. They have some kind of search representation, visual representation of the bytes that you search. So I just got a random binary, and I looked for FF15. That's a Carrera Duart, if I'm not wrong. And this is the distribution of the occurrences of that pattern. In red, between red, is the text section. And as you can see, there are no hits outside the text section. And it's a really simple pattern. Probably it's too short. But it's a really good indicator of code density. We will be using patterns that are more tied to not code density, but compiler-generated code density. But I think this gives you the idea. So how we selected, actually, the patterns, the genes. So you can think like we have a gene pool that is a set of all those compiler common patterns that we know. And then for each like candidate, we do the pattern matching over non-packet, like the binaries we had before, and packet. I'm talking about in disk, not in memory right now, okay? So the point is like, oh, we got a pattern that has a really gets a lot of occurrences on a non-packet binary and gets 0 looking inside a packet binary. So this looks like a good gene, so this survives. I got another pattern that has really a lot of hits on non-packet, but also a lot of hits on packet. So this giving no information to me. So nothing, and obviously if it works with packet and not with on-packet things, it's even worse. So that way we started to remove some patterns, add some new others, and get a sample that was working for all the compilers we were working with, and that were good enough to have a really nice indication of compiler-generated code. So how we used those patterns, how we use those patterns during the unpacking process. And this is where all these things are mixed with the Python thing. So we can think as a packer as something that has a binary that has another binary inside. It's serious stuff, come on. So the unpacking process will be something like this. And if we like have some, if we have a way to count the, stop looking at the pregnant woman for a second, come on. If we are able, looking at the memory and count the occurrences of the patterns we have, we will have like, during the unpacking process, we'll have like a growing, well, mostly changing, but we can imagine like growing until it stabilizes, close when the unpacking is finishing to reveal the original binary. And yeah, then we have the jump to the original entry point. That
He wants to know if we don't see the fucking further.
I have some videos, we can watch them later. Yeah. Tonight in the party. Yeah. So we want to like stop or decide that it's done as close as this point as possible. You know that sometimes it's not possible and you have to jump to the original entry point in the subway or in the street or in the ambulance. But this making like actual heuristics, this looks like this. This is an UPS sample, and this is how our heuristics measure the amount of compiler-generated code that the binary has over time. Time here is like a number of instructions emulated by box. So this is funny to see because you can see that in this case it's growing, changing a bit, modifying, and we have a really important drop of the before like stabilizing. That's virtual free. That's the packer releasing the memory he's been working with, like the dirty memory that I'm working with this and to unpack the stuff. So that drop is the virtual free. So it's nice to see this in this simple way the work of the packer. So this is UPX. This is, for example, Timida. This is really if you can see the process is quite different, but the stabilization thing is similar. And if you look, the graphics are not in scale, but if you look at the actual scoring that we give to the amount of compiler-generated code, you will see that Timida the scoring is quite lower than UPX. What does mean? That means that Timida destroys more or obfuscates more the original packet thing using virtualization, obfuscation, whatever. But the important thing is that the stabilization is the same. I mean, we have it and it works. And in case you are wondering, if we have like a double packet sample, it's like this. Okay, so you can recognize the first virtual free, sorry, from the first packer and the second step of the second packer. The stabilization is the clue here to get the right point. But there's a problem with that. So when we know that the code is stabilized, I mean, we have like a graphic and like the ones we were watching before, and when how we decide when the graphic is stabilized, the scoring is stable enough. So we solved that by using by the sampling frequency. So we have a sampling frequency that in some way with let me come back to we can easily recognize that we have like two kinds of packers here, things like this that are changing a lot and then not doing nothing, and what we can call some kind of slow or lazy packers that the changes are really slow a long time. So we have like a minimum we request for the unpacked sample to have a minimum amount of code. That will be like requesting that the baby has a minimum weight or height or something like that. So with that and the sampling frequency we use, we actually got in not far from the original, to jump to the original entry point, but as Eero said, answering a question, we are not that crazy about getting to the original entry point. We get close, and if we were interested, we can get closer using more computation. But right now, it's what we need. So this was the theory behind the stuff, and I think Eero is going to show now a demo with the actual, this thing work inside VS Class, so we are going to see how this thing works inside. So, Eero? Yeah, well, just giving a bit of what you are going to see. We are going to run the test inside the virtual machine, inside this laptop, but the actual tests have been done with an iMac i7 with a virtual machine with 1 core, 2 gigabytes of RAM. It's not much, but it's enough. The minimum unpacking time is 5 seconds, actually. That's basically the 3 seconds or so for Box to restore the snapshot, and 2 seconds of unpacking. Of course, with things like Temaida that require like 100 million instructions or even more, we go to the 20 seconds, maybe 20, almost 30. So the average we got over, well, it's 580 packers. I mean, I'm considering here like different packers, like the same UPX with no compression, UPX with maximum compression. So that's why the number is so high. There's not almost 600 different packers. I'm including that. So the average we got in those tests is like 10 seconds, 11 seconds per sample. So now, just...
Although probably there were like at least, I don't know, 50 or 100 different packers, right? I mean, there were many different packers. Then there were all the different options.
Probably
but
200.
Okay.
But
it's rather generic. This class. So what I'm going to show you now is the web interface we have for our big ass system that does all this unpacking and malware clusterization and all of that. So that's a topic for another thing. But we're just going to use that. We developed this technology to be part of the unpacking process. So I'm going to use the GUI to show, how we submit some samples, well, that we have submitted already, and how the unpacking actually happens. So let me work with the sizes here, with everything. Is that readable? Yeah. You can read that, right?
maybe too big. Yeah.
Readable? Okay, so the thing is, what you're seeing right now, it's the interface where I've submitted like a set of files from our test set, and everything is just not doing anything yet. So what I'm going to do now is I'm going to start the unpacking thread, the unpacking process in the VM. The good thing is in this massive system, we can start as many unpackers as we want. So we can eat many samples, an hour a day or whatever. So, and then they get clustered and everything according to their code. But so I'm going to start it. And you should be seeing some of these things. Yeah.
Yeah, the first one started unpacking.
Okay. So, okay. Running on a VM, so this thing may be a little bit, it's not as fast as in other places, but you should be seeing like this unpacking thing actually there. Changing little by little.
Yeah, the first unpacking already finished. It was VM Protect, and we included here. You can maybe it's a bit hard for the people in the end, but we included the the initial scoring that we give to the binary, that is 0.5, and the binary where the scoring that where we stop it when we found that the process is stabilized. So it's 8.3. So also we have a import address table related pattern that we use for like help to know the unpacking process. But yeah, we are. That's some information. I think we can take a look at the. We can just download an IDB from VS Class, and I think we can take a look at one of the samples that we already got.
The cool thing about the system is as it finishes unpacking stuff, you can actually, from the web interface, look at the memory dump and actually take a quick look to see if there's strings. You know, that's a good, quick way to, you know, to have a sense whether it's unpacked or not. And then download the IDBs because, you know, after this stage goes on, there's an IDB that is generated out of it because we have IDA and everything running inside, and just to appreciate the quality of the unpacking. So that's what I'm going to do. I'm going to cheat a little bit here because we already pre-downloaded something, otherwise it will take forever. Let me get the other VM. Prettify a little bit this thing. Let me see if I can make it full screen. No. So that's actually just coming straight out of the IDB that comes straight out of the machine. And this is a VM Protect. What's this one?
Yeah, this one.
And you can see that the code is decent enough that IDA then recognize what's going on in here and could apply the flirt signatures. And so we actually end up having a lot of nicely defined things. And cool thing is there was absolutely no human interaction in just dropping the executable and getting a nice, clean, mostly analyzed IDB. So, and we're talking about a decent packer, so it saves a lot of time. And the good thing is, as he was explaining, nowadays because before we used to run just for a long, save long enough time that we would actually be certain, more or less certain that we would get the thing unpacked. But nowadays, given these last heuristics, we're able to pinpoint pretty closely the point in time when the thing is unpacked. So it saves us a lot of time, plus leads to much cleaner results because the application has just started. There's much less heap to take, much less like random noise to worry about. So those are the results. And so about issues that you might find with this, that, possible problems, but they're actually not so. Packers with compiler code, but as he was talking about, the way we measure and the way we measure differences is not really that much of an issue. You want to say something?
Yeah, the point is that we don't care if, it's what we care is that with unpacked code on memory, our scoring, the number of genes that we detect changes. So we don't care if we, at the 0 instructions emulated, we're here or we are here. We are just looking at the changes and waiting for the changes to stop. So,
yeah. And then the same with like multiple stage or impact files. Most of the, I think all the tests that we have done, we haven't found any issues with it. So I mean, those are common problems that ended up not being such a problem for this new system. And then obviously there are problems that are actual problems, like virtualization, like when you have something like the Midas, Enigmas, or VM Protects, and have like heavily, code in the produced for the VM. That's something that our patterns don't work there, and there is nothing too obvious that we can do to get around it. And same with obfuscations. Do you want to say something? I don't know if you want to say something about. No.
Yeah, just that with obfuscation and whatever the virtualization, we always have some like original code constructs that it's what we like it to call the selfish code because it lasts. Even if the packer is really nasty about that, there are still some patterns that we got. That's why Temida works, that's why VMProtect works. And obviously, anti-disassembly doesn't affect us because we are looking at byte patterns. So we are not disassembling and working, we are just byte
just looking at raw byte patterns. Then obviously, as I mentioned earlier on, packers that actually do their work on demand, and at no point in time there is the whole thing unpacked, as well pose a little bit of a challenge, because we might not be able to measure exactly the right amount of code, because it keeps changing a little bit. Even the application is officially, well, not officially unpacked, it's still going. So those cases are a little bit, messed up. There are a couple of things we can think about how to work around these issues, but so far, given that most of the cases are of the other type that we already dealt with, okay, that's for another day. REcon 211. Then, work in progress, we would love and we will try to make at least the unpacking part of the system that we showed you available online in some form, because it works. So it would be really cool if people could just upload files and get the unpacked files to work with them. Plus, obviously it's a commercial product, but if we could actually make that part available, it would be really neat. Then plugins for the system, it would be really nice to be able to, for some really, really, really simple packers, be able to deal with them a bit faster, just because if we know what they are, just deal with them right away, instead of running them through all our system, which is cool but slow. Then having things to deal with obfuscation specifically, and virtual machines. Probably most of you have read the Rotalume paper, this tool for automatic reverse engineering. That was from the Carnegie Mellon guys, and I think there was some Italian guy from the Politecnico di Milan in the middle as well, which they came out with a really, really, really neat system using data flow analysis, tracing, to actually have something that automatically extracts, automatically discovers the emulation loop, automatically discovers the opcodes of the virtual machine, and is able to reconstruct the control flow graph of the virtual machine code without human interaction, which I think is super neat. So it would be really nice if this kind of practice and technology standardizes to have something like that in our system. And then obviously support more OSs. Right now we're centered Windows XP, SP2, SP3. It would be nice to expand that and use other technologies that will give us a little bit more speed other than Box, but we are lazy. Point of the talk.